Hello, everyone. Welcome to the Guaranteed Safe AI seminars. I'm Orpheus, founder of Horizon Omega, a nonprofit focused on AI safety facilitation. The purpose of this monthly series is to accelerate the Guaranteed Safe AI research direction. We have 1 hour, maybe more like 55 minutes. Usually we have it's half presentation, half discussion. We can have the Q&A during the talk. And today we have Jobst Heitzig, senior mathematician AI safety designer, with a talk entitled Model-Based Soft Maximization of Suitable Metrics of Long-Term Human Power. Thanks so much for being here, and so the floor is yours.
Yeah, thank you for having me. And I aim for about 30 minutes presentation. I have a lot of backup slides, but I'd rather have a good discussion. This is all about power. I would claim power is at the heart of AI risk because AI power seeking is an instrumental goal. Loss of control is what we want to avoid. There's the global AI race, which is also about power between entities, countries, labs. We have this gradual disempowerment paper recently I can really recommend. I believe this is already happening now. So power is really at the heart. And it's not only about the AI grabbing power, but it's also us handing power over voluntarily. And so there's a number of course, proposals how this could be avoided. And I run through them really fast because you probably know all of them. I just liked this IASA conference in February and I took a lot of notes. So I want to quote some people like Joseph Stiglitz, and he said, AI should augment labor rather than replace it. So this is also about a power relationship between workers and AI. Stuart Russell says, we should not aim for a fixed objective. We should make the AI learn and update the objective by observing humans. So this is also engaging, keeping some power to humans to shape the goal. I don't believe that this approach of assistance games and inverse reinforcement learning really works because, first of all, I don't believe in utility functions, and I think goals are changing, and even if they were not, preferences are really not identifiable. But otherwise I like the approach. Then there's Max Tegmark, you all know. He says, we just don't build AGI, we just build tool AI. Well, it could work, but I think the public wants AGI, so maybe that's not an option either. Then Joshua Benju says, we don't build any agents. We just build scientist AI. Well, being a scientist myself for a number of years, I believe, yeah, scientist AI is a good idea, but it's not true that this is not agentic. A scientist AI that answers questions such as what would happen if we pump another 1 billion tons of CO2 into the atmosphere and gives me a 1,000-page report. That is an agent because the way it writes the report will have a consequence in the real world. So I don't think we get away with non-agentic AI. There's no such thing as a non-agentic AI. Geoffrey Hinton recently said the AI should have motherly instincts, love the humans. I don't think this is a good idea because this would be rather paternalistic or maternalistic. We will not end up with having power. We will rather end up as in WALL-E, I guess, being cared for, but not making any real choices. So this is really a horrid story for me. But they all have in common that they recommend not just maximizing some utility function, some given utility function, which sadly seems to be the preeminent approach at the moment. So if those approaches are not what I think is correct, then what else? And there's one thing I really like. This is the idea of corrigibility. And of course, you all know this means the AI should be corrigible, that people should be able to correct their behavior, stop it, give it a different objective, say veto what it does, so on, but also the AI should maybe ask for confirmation and so on. I think this is a really cool idea. I just don't think it's enough because we will still have inequality if the AI is corrigible and gets into the hands of the wrong people. That will increase inequality. And by default, the AI will be in the hands of the wrong people because it will be in the hands of the people who have already a lot of power, and then they will get more power. So corrigibility is not enough, I think. There's also Maria Ressa, who cautioned us that AI also threatens social peace, which is also to do with inequality. And of course, it can be misused by some people who want to establish a totalitarian regime. And I think this is really not out of the question. So I would call this the risk of misuse that remains if we have a corrigible age. And this is what I want to address in this talk. So before I do that, I want to take some really shameless commercial here, advertisement, or not commercial advertisement, because in my free time a few months ago, I asked Claude to write a few novels about AI safety with me. And I actually think they're really good. So if you scan this QR code, then you find 6 free novels and a few short stories and 2 plays, all written by Claude and me, which also explore all these approaches by these people that I just told you about. So I think they're really fun. Please give me feedback if you don't like them. Okay, so I believe the approach we should aim for is something like this imagined product, EMPO, the AI that doesn't patronize, doesn't just serve, but it empowers us and everyone. So this is kind of the commercial pitch here. And now we get to the core. How could we even do that? And this is kind of the preview of all the equations that I might or might not get to in this talk, probably not get to all of them. And so what you see more or less immediately, it looks similar to reinforcement learning. It's a version of reinforcement learning or dynamic programming. At least you have a number of equations that look awfully like Bellman equations, and that's true. But you also have some things that looks strange, maybe. And this is the approach that I'm going to pitch now. Let's see how deep we can do that. Just to give you some ideas what these ingredients here mean, there's something like social norms represented by action priors here for humans. Then there's habits involved, which is also something like a default policy for humans, and bounded rationality. So this triple of ingredients here is meaning to represent human behavior in a, I guess, more realistic way than other models, like, for example, the assistant games approach or the inverse reinforcement learning approach does, because they assume humans are rational mostly. So my robot that I envision will not assume humans are rational, but boundedly rational in a certain sense. Then there is some ingredient which is a little bit strange, which is meant to incentivize the robot to make commitments. We will see this later. Then there's some things that are related to soft maximization, like, for example, here, the policy of the robot will not be a maximum, an argmax. It will be some form of soft maximization. Not a Boltzmann one, but a power law one in this case, and I'm going to say why. And then very crucially, the AI is not considering humans having a fixed goal or just wondering what the actual goal of the human is, but the AI will just wonder what could humans achieve if they had whatever goals. So it is imagining a very wide set of possible goals that the humans might have. And because that is kind of the essence of being powerful, is the ability to reach all kinds of different goals if I wanted to. And there's some things that relate to the aggregation of these things. For example, here, we sum over all the possible goals, and then we also sum over all humans. But we're not utilitarians. We care for risk aversion and inequality aversion. So that's why we have some functional transforms at play here, also power law shaped with some exponents that introduce some risk and equality aversion. And these are also parameters that we can use to tweak the behavior. And then finally, we do not only care for the current power of humans, but also for power in the long term. We want to preserve the power. Okay, so this was the preview. This is the paper if you haven't followed the link yet. And now we can soon go into some details. Before we do that, I want to relate this very shortly to the other approaches that I told you about, because I think there are certain relations. So this EMPO approach, if you want to call it that, I think it is related to this labor augmenting AI idea, in the sense that the AI will not just do what it thinks is best for people or just take away jobs from them and disempower them in this way, but rather enable them to do their job way better than before. It is related to scientist AI in the sense that it relies on a good world model. So the thing that Yoshua Bengio produces with law 0, I think that should play the role of the world model of the AI that the decision algorithm that I design or someone designs is using to make predictions about the outcomes and using for model-based RL. It's in a sense also related to tool AI, but not in the specialized sense of Max Tegmark, but rather in the sense of the AI that follows this objective will turn itself into something like a universal tool that allows people to use it for all kinds of things, to reach all kinds of goals. And obviously, it doesn't maximize a fixed objective, at least not in the classical sense of utility theory, because the thing that it softly maximizes is not it's not a property of the state, but it's rather a property of the dynamics of the whole model. And then, in a sense, it also evolves at least some maternal instincts, at least those instincts that are related to empowering the children, to give them information, to make them make better decisions and so on, but in a non-maternalistic way. Okay, so the paper has explored a number of possible consequences of the approach, and there will be a number of emergent behaviors that I think are really interesting because they point to the safety and also the usefulness of the approach. The first thing is the robot will be incentivized to make binding commitments, telling humans what it will do in reaction to certain actions by the humans or in reaction to certain commands or button presses or whatever. So it will be transparent about what it will do. It will mostly obey, not always. And there's some cases where it won't. It will ask for confirmation in some crucial situations, especially when there's a potential irreversible side effects. And it will also kind of extend the menu of choices that people have, but only to a certain extent because it doesn't want to overwhelm people, because giving them a million different choices, knowing that they're boundedly rational, will not improve their decision-making. It will obviously remove obstacles to make kind of way for humans to reach more places on more goals, and will also protect them from harm, because when you're harmed, you're disempowered, you can do less stuff, especially if you're dead. And it will provide information, because information increases the ability to reach goals that I have. It will also improve or aim to improve the cognition. Of course, all of these things only if it can do that, right? If it can improve the cognition by, for example, calming the person down so that its level of bounded rationality goes up, then it will do that. And it will also tend to avoid irreversible change because that narrows the possible trajectories and so on. This all looks nice. It will also improve collaboration between humans because then they can reach more goals, especially also collective goals. And most importantly, it will probably not take over. Of course, many of these things are hard to formally prove because they're somehow vague statements. So this is just trying to give you a glimpse of what I think will be the consequences of this approach. Some of them I have studied a little bit more formally in the paper. I won't have time to go through them in detail, but maybe to give you some intuitions later. Okay, so if you want to work with me to make this happen, especially if you know about reinforcement learning or even maybe multi-agent reinforcement learning, then please talk to me because I have almost no funding. And I really want to pursue this further, but I can't do that alone. Okay, now let's take some time to focus on details in the remaining almost 15 minutes that I want to talk. Unless there's urgent questions already now. Are there any urgent questions? Okay, it doesn't seem like that. So you saw this picture already. And now I want to try to motivate these formulas by, in a little bit axiomatic way. So I also work on social choice theory a lot of times. So I'm a fan of this axiomatic method, which says I have these desiderata or even axioms that I want something to fulfill, some method or some voting method or some system. And they're not just a full spec, they're just individual things that I desire. And then I try to derive certain design choices from that. Sometimes unique, sometimes not unique. And it's kind of a modular approach to designing aspects of formulas, which I really like because it allows us to also motivate things really well, I think. Okay, let's look at a toy example to give you an idea of what the challenges are in designing a metric of human power. So let's assume a really simple toy example where the AI is a rocket and it has to evacuate humanity from Earth because Earth will explode, and it can take us to either Mars or Venus, but just once. And now let's model the world in a really simplistic way and assume in this decision node the robot could either just take us to Mars or take us to Venus without asking, just making a choice, a utilitarian, assessing how well humans would be off on Mars and how well they would be off on Venus, and then just get them there. Or it could wait until humans press one of two buttons, which it has on its chest, a red button and a green button. It could plan to take humans to Mars if they press the red button, and to take them to Venus if they press the green button. If it doesn't tell the humans this plan, then the humans having this choice, formally they have the power to decide where they go, but effectively they don't, because they don't know which button does what. This is also a crucial distinction between the metric I'm going to develop here and some alternative metric that is in the literature, namely, they even call it empowerment. I think this is not a good name for it. It's the channel capacity between actions and states, because channel capacity between actions and states would already indicate that humans have some power here, whereas my metric would say, no, they don't have any power here, unless the robot also tells them what each button will do. So and this is the thing about the commitments. So the robot, if it can make the commitment to get them to Mars once they press the red button and to Venus instead, then humans will know what each button does, and then they really have the power to make that choice. Meaning, in game theory terms, they will have in their information set, they will have a policy that they can use to get to Mars with probability 1. Even better, I believe, it would be if the robot shares first all the information about the consequences, what they will find on Mars and Venus, because then they can make a better choice. So what I want is a power metric that assigns a number to each of these decision nodes that the humans might end up in, each of these states. And this number should be largest in this lowest state here, because it should measure how much power they have, and it should be kind of considered largest in this node here. So that's a challenge, how to define this metric in purely structural terms. I want the metric only to depend on the transition probabilities of the stochastic game model, and not depend too much on understanding semantics and meaning and so on, because I'm really skeptical that an AI really can understand well enough what these things mean. Okay, so how exactly can we do this? So this is kind of now the recipe on a high level. So there's, of course, this thing about the world model, which is not my topic here, which is Joshua Benger's or other people's job. Jan LeCun is also doing that, and many people doing this, world models. And let's assume it has a world model that's basically something like a stochastic game. So this is given. And of course, it's updated on observations all the time. Now, how does the robot make decisions? This is what I care about. It should evaluate all, maybe not all, but a large number of possible policies for itself. Maybe if it's a large action space, then of course we need some search and so on. Or maybe we need to learn this policy. But in theory, imagine it could evaluate all of its possible policies. And how does it evaluate its possible policy pi r? Well, first of all, it looks at all possible future states. Again, this can only be done in a small environment. In a large one, we would have to employ some search or learning again. But these are implementation details. I don't want to focus at this moment. Yeah, so it looks at all possible future states and all humans that it deals with, and all possible goals of these humans, considering they might want to get wherever. They might have all kinds of weird goals. So this is, again, coming from a large set, which we might have to sample from in practice. But let's assume we can do this triple nested for loop here. And then it would consider what the human might do over time if it starts at the state and tries to achieve this goal, given that the human is boundedly rational. And it will basically calculate or estimate or learn something like a value function for this human in this state, given this goal, and given the candidate policy of the robot. candidate policy being something like, I commit to these button meanings, or I don't commit to these button meanings. I share the information or I don't share the information. That's the robot policy. So we get a lot of numbers here, a very large tensor. And this models how well that human can achieve that goal if the robot acts like this, in this state. That's basically very high dimensional thing. And of course, we have to aggregate it now. So we first aggregate it over all possible goals of that human in that state. And that gives us a metric of the human's current power in that state. And it will turn out this will be a logarithmic quantity of a logarithm of a sum, because it has nice interpretation. And that measures how well the human can achieve any type of goal if the robot acts like this. Then we aggregate it further across all humans, because we want, well, empower everyone. And we do that in a certain way, not just summing it up. And the resulting thing is a number that now only depends on the state and the policy of the robot. And it will be interpreted as the intrinsic reward to the robot that the robot now aims to increase over time. Okay, and that represents how well humans can achieve goals from state as on if the robot acts in a certain way. And then finally, we aggregated, this is no longer very surprising, across time, because we want also future empowerment. So that's why we treat it as a reward rather than as the value for the robot. So we're aggregating it over time. And then because the environment is stochastic, we're also aggregating across the uncertainty. And this gives us the basically the value function for the robot in a certain state. And then we choose a policy that softly maximizes this. Okay, so that's a high-level program. And let's see how many details I can now motivate before it gets too boring and you want to ask some questions. Okay, let's focus on the first step. How do we even measure a human's goal attainment ability in a certain state, given a certain goal? It might seem obvious how to do that, but given that the world is multi-agent, there's many humans, it's not that obvious. A game theorist might think that we should solve something like a game between all humans and the robot, where the policy of the robot is fixed and the policies of the humans are then mutually optimal. That would be treating humans as perfectly rational. I think that would be bullshit. I think humans have more or less fixed beliefs about what others will do, encoded in social norms and habits and so on. So our metric deliberately does not aim for kind of finding something like a Nash equilibrium or something, but rather getting at a more realistic assessment of what humans will do. And that will depend on what they believe others will do. And I'm taking a very, very privileged and convenient stance here, because I assume that the world model is good enough to tell us about social norms and to tell us about these beliefs. So I just assume that we know basically what humans believe about each other and what their habits are and so on. So we can use it to model what they will do if they had a certain goal. And of course, we want the whole thing to be efficiently computable from a world model or learnable. And therefore, we really use a value function as in standard reinforcement learning, fulfilling a Bellman equation that allows us to do this recursively. That's not so surprising. And maybe a little bit more surprising, later on, we want to be able to aggregate this across humans. So we should think about the interpersonal comparability of utility, which is a hard problem in philosophy. So maybe we should really make this underlying reward model for the human that tells us what the rewards in state S prime are if I have the goal GH. Maybe we should make it a very simple thing, maybe even a binary variable that says goal reached or goal not reached. Because then value function is basically nothing else than a probability, the probability of reaching the goal. I mean, there might be some discounting here, so it's not really a probability, it's something like a discounted probability. But essentially, it's probability and it's bounded between 0 and 1, and it can easily be compared between humans. So, so that means goals should be encoded basically as events in a probabilistic probability theory sense, a set of possible outcomes or set of possible trajectories that that encode when the goal is fulfilled versus when it's not fulfilled. So this is the type of goal. You might think this is a really simplistic type of goal. And yeah, really, this is very simplistic. But I think it's okay because the aim is not to cover the actual goal of the human. The aim is to cover a very wide range of possible goals. And so the width is more important than the accuracy here. So for example, we could assume every possible subset of the set of trajectories is a possible goal. So that's a large set of possible goals, but the goals themselves are very, very simplistic. Okay, so some example how these commitments could come into play then. So let's assume the robot has k buttons, more than 2, and it can label these buttons. And the labeling would be a commitment, right? It would tell the human what would happen if you press this button. And now, basically, what I think it will do, and I haven't proved this yet, but it's the strongest intuition, it will look at the goals, the set of possible goals, and maybe the set of possible goals allows for something like a clustering. And there might be groups of goals that it can support with a single policy, and another group that it can support with one other policy. So it will basically, I think, do something like a k-means clustering of the goal and policy space to figure out k different clusters of goals that the humans might have and a corresponding policy for itself that would support these goals. And then it would label the k buttons accordingly and allow the humans then to pick a fitting policy for the robot that fits their goal. One of these policies might be follow me around and see what I do and do the same. Another would be get out of my way because I want to concentrate on whatever. Another policy might be go about and collect as much money as possible, and so on, right? Generically helpful policies that help certain types of goals of the human that the human might have. Okay, that was an example. So now we have to think about how to aggregate this, and I won't be able to go through all of this before we enter question and answer, but to give you a flavor of how I decide how this aggregation should work, let's look at the first step of aggregation, namely aggregating across goals. So we're still with a single human in a single state and assuming a certain policy of the robot, and we wonder how to aggregate these individual goal achievement probabilities, V. Okay, so we want this to be quantitative, obviously, and now we assume a number of desiderata or axioms that are very similar to what welfare theorists would do to derive a welfare function. So you could even interpret our function in the end as something like a welfare function in terms of power rather than in terms of wealth or income or consumption. And one of those kind of very popular axioms is an independence axiom. It means basically if there are certain unaffected goals which can be reached reached just as well, no matter what the robot does, then they're somehow unaffected by the policy of the robot, and then we should be able to kind of more or less ignore them. And this is not really a formal written down of the axiom. It's a little bit more complicated, but this is the spirit of the axiom. And if we require this axiom, then we need to make this aggregation function WH that aggregates all these individual value functions here. We need to make it separable. Separable meaning it's a certain transform of a sum over all goals of another transform of these values. So there's an inner and an outer transform. And now what should these transforms be? Now another one that I have is, we're talking AGI, right? So humans are involved in all kinds of different things. Maybe they're wondering what to do in the household and then what to do with their finances and then what to do on their job. Or the human is playing 2 different games. So it would be nice if we could, in the analysis, focus on individual parts, sub-goals. And therefore, it would be nice if the total power that a human has is somehow a sum of the powers that they have in the independent things, at least in the case where these situations were really independent. So that's a nice axiom, because if we require it, then it immediately tells us that the outer transformation, big F, needs to be a logarithm. And so without loss of generality, we can make it a logarithm to base 2, and because that gives us a nice interpretation of the whole metric, which is namely something like a certainty equivalent effective number of binary choices measured in bits. Okay. We also want the whole thing to be independent of a certain operation that might happen. So let's say our world model has missed to model a certain thing that could happen in the world that would change everything. Well, like in this in this game environment, there might be a storm cloud, and they have to abandon both games at the same time. And the world model doesn't contain this possibility, right? But it has. Let's assume it has a certain probability, and now, if we were to include this possibility event, then not so much should change, because this event should, in a sense, if we assume it affects everything in the same way, all of the goal-reaching abilities go down by a certain factor, let's say by a factor of 10, then the policy that is optimal should be the same policy. And that's a good intuition. And if we require this, then it means that the inner transform needs to be a power. So now we have figured out basically what this aggregation over goals must look like. It must be a logarithm of a sum of some power of the v. Now, what power? Now comes uncertainty aversion or risk aversion. If we want the robot to be rather trying to make the world more deterministic, or focus more on giving people the option to choose from 2 things that they can reach for sure, rather than 4 things that they can reach with 50% probability, then this exponent needs to be larger than 1. And so the simplest choice for something larger than 1 is 2. So why not go with 2? Actually, if we set this exponent to 2, we have another nice property, namely this WH metric will be between minus log 2k and plus log 2k if the world is a banded situation. So this gave you an impression how I derived these explicit formulas, the ways to aggregate these formulas. And for the other levels of aggregation, there are similar things. But I want to stop here to allow us some discussion. Thank you.
Question. If you would want to implement it, then what would be your first steps and what would your next steps?
Yeah, if I implement, you mean in a test environment, like kind of a pilot application to show that it works, then I would say I would find a partner such as maybe an autonomous vehicle company like Waymo or something like that, and try to make a pilot application that uses their world models that they have already and replace their current decision algorithm with this decision algorithm to see how this system would actually act in the real world. So that's actually what I plan to do down the line, maybe next year, maybe in 2 years. Before that, I would probably have to do a little bit more testing in larger grid world environments, because in the paper we just used a very, very, very simple grid world environment. So does that answer the question, or did you mean it differently, Roland?
Yes, I guess it did.
Okay, good. David.
Thank you.
Hello, thanks for the talk. How important is the AI's ability to communicate its policy to the human? And it's not really covered in the math, but it seems pretty important if a human's going to make an intelligent choice.
I don't think it's absolutely necessary. We can even imagine an AI that cannot talk to humans at all and is just operating in the background and removing obstacles and protecting humans from harm and so on. And that would already be quite useful, I believe. Max Tegmark, I think, has this concept of the protector AI. And I think that would be amazingly important already, but really, really useful as in terms of like a good assistant. Of course, the AI needs to be able to talk to the human, right? Tell it what it will do. They need to discuss what they're going to do together. And so, yeah, I think your intuition is right, that if the AI cannot label its buttons, then it can be less helpful than if it can. I think it can be just as safe, but it can be less helpful.
Thanks.
So there's also
Another
one
question.
sorry, and let me add one more sentence to this. I think one emergent sub-goal arising from this objective is to actually improve the communication abilities, to learn the language of humans, or to make humans learn the language if they can't speak yet. or to, I don't know, to increase the channel capacity between them for communication and so on.
The other question I have is that in one of your slides, you indicated that you are interested in LLM expert, and I'm wondering how would you integrate this approach with LLMs?
Yeah, right. That was unexplained. So at the moment, I have no access to a really good world model that is general. But eventually, I want to kind of make some tests with a really general setup. And so I have this idea that LLMs basically have likely learned a lot of knowledge about the real world, and we might be able to make them give us decent world models on the fly, maybe in hierarchical fashion. For example, if we ask the LLM, I'm planning to give this talk, please give me a few action options that I could do and the possible consequences of those options in the following JSON format. And then in the next step, I would ask it to quantify the transition probabilities. And so I think they can come up with at least good toy versions of stochastic games, small discrete stochastic games. And then if you use a hierarchical approach, then once you selected one high-level action, then you can ask it to drill down and to increase the resolution and to get to the next a finer level of the model hierarchy. And I want to test this out, but I can't really do that because I'm not an expert in how I should prompt the LLMs. Of course, I could have an idea how to do it, but I would rather like to work with someone who really knows how to do it well in order to test this hypothesis.
Thank you.
Hello, I've got another question, if you can hear me all right.
Yeah.
Now, what's the relationship between the AI that asks the question and then the subsequently modified, perhaps, or down selected or something? It seems like once the button is pushed, there's a new policy running. So how do we think about that, if this makes sense?
Yeah, I don't think it's a new policy because a policy specifies what to do in all possible situations. And when the humans have pressed the red button, that's a different situation than when they have pressed the green button. Sorry, I tried to get to that slide, but I moved in the wrong direction. So I think the slide is somewhere here. So policy would say, in this situation, the policy for the robot would say, first of all, which of those initial actions to take. So either acting directly or making or waiting for the button press, or making commitments and waiting for a button press, or informing and then waiting. Okay, that's the specification of the policy, but the policy would also specify which action to take once they have pushed the red button after not having been informed what the buttons do, and what to do if they push the red button once I have made the commitment. And all these decisions are encoded in a single policy, right? Policy is a map from state.
I think maybe what I'm thinking then is what happens over repeated interactions. Has the literature gone there in terms of learning, continual learning over repeated interactions?
You mean that the whole game is played repeatedly?
Yes.
I don't think that happens at all in the real world.
Okay.
At least not in meaningful. I mean, of course, they can play a lot of chess games and so on, right? But I mostly worry about situations that are once in a lifetime, right? That they never get back to. They might have encountered similar situations in the past, but to really learn from that, of course, I mean, you could say, in this situation, the humans typically wanted this, and it was typical, and they made these choices typically. So I'm assuming the next time we go to the restaurant, they will order the same dish. I think that's nonsense. Humans are not like that. Not in meaningful situations. So this is why I'm taking this maybe extreme view that trying to learn the preferences of the humans, that we shouldn't rely on that because it can be too wrong. But of course, we can debate this. So George Russell will probably have the opposite opinion because he believes in this assistant game and inverse reinforcement learning thing.
Okay, thanks.
We also have a question from Harry. Do you want to speak it out, or I can read it?
Is it in the chat?
Yeah, so I'll read it. All right, no problem. So the question is, you mentioned corrigibility, given that the agent's optimizing is optimizing based on its beliefs about human goals, would it want to resist changing those beliefs?
Yeah, so I have to set this right. It is not forming beliefs about the goals at all. That's the main difference to the assistance game thing. The AI is not wondering what the goals of the humans are. It is not trying to learn the goals. It is considering that the humans might want whatever. It has this very, very large set of possible goals that it always considers, and it's ignoring any information that that the human might want this or might want that, because, as I said, it's an extreme assumption that is too unreliable. So first of all, so this is about this assumption. But let me still try to make sense of this. Would it want to resist changing those beliefs? Yeah, it doesn't form these beliefs, so there's no meaning of changing the beliefs. Does that answer the question? I mean, of course, it has this set of possible goals, and if it's too narrow, and at some point it has information that humans might want something else that it hasn't considered, then of course it should widen the set. And this is something I haven't really thought about, because I'm always assuming that basically it has this world model which has large number of states, and it considers that the humans might want to steer the world in any one of those possible states. So every possible goal that they can conceivably have, it is considering. In practice, of course, we have to sample from that, because of course we can't go through all of those goals. We can only do something like stochastic approximation of this integral over goals, or set sum over goals. But I think that's fine. That's just an estimation problem. Okay, Robert has another question. If you would implement this, which features would you implement first? Which features next? Well, I think it should be implemented as it is. I mean, it's not hard to implement this algorithm, right? Because if you have a small enough world model, you can basically hard code these equations, and you just compute them by backward induction. That's what our research code does already in the small environment. It gets interesting when the environments are larger, and then you have to use some form of multi-agent reinforcement learning to learn these things. But the way they're written, you can basically use off-the-shelf RL algorithms to try it. They might not converge well enough, so you have to tweak them, of course. But in a sense, it's not rocket science at all to implement this. The hard thing is to make it scale, I guess, and to see whether it's really beneficial. And to get good enough world models.
Hey, Jobst, I think maybe one of the things I'm not quite clear on is, you say this model doesn't form beliefs about human beliefs.
Oh no, it does form beliefs about human beliefs. It doesn't form beliefs about human goals.
Human goals. I'm sorry. Thank you for correcting me. Okay, so if that's true, what happens if we want this agent to interact in a sort of multi-step way, where it's an agent that's helping a human accomplish some task, and the human is sort of figuring that out as they go? What can you kind of give me some intuition about what that would look like?
Yeah, I think it's basically via this commitment thing. So it will commit. For example, the robot might commit to doing certain things when the human says certain words. And so it doesn't need to know what the human wants. It will just obey the command because it has committed to. And it knows, because it knows that making this commitment will allow the human to reach more goals, and therefore will make the commitment.
Okay, would it be fair to say one option it could offer the human is I'll do exactly what you say, or another could be, we're talking about the rocket example. So an engineer that knows that a human shouldn't put the engine in an unsafe state.
Yeah.
Kind of like a car with traction control or something like that. Do you see what I mean by that?
Not exactly. Are you saying that it should not always obey, or it should make statements like, I will do what you say except whatever?
Yeah, I'll do what you say unless you put the rocket in a condition such that it would, break apart, or you would deplete your fuel too quickly, that sort of thing.
Yeah. Okay. Let me show you this example here. Where is it? So for example, let's assume that the human gives a command that would get the world into a really narrow situation. It would have a lot of irreversible effects. And the robot, knowing that the humans are boundedly rational, it will assume that the human might not have meant what they say. Well, it might have made a mistake. And if the consequences are really disempowering for later, for other people later, then it will try to trade off the obeying the command all the time with the likely disempowerment that it will then cause. And the larger the later disempowerment and the lower the assessment of the rationality of the human giving the command, it will ask more often for confirmation. And for some things it will actually reject doing, like, for example, a human killing themselves. It will most of the time reject doing that because the loss of power later outweighs the increase in empowerment due to the obeying the command. So there are these trade-offs, and therefore it's not easy to say that they will always obey or not always obey. So it's not like the laws of robotics that there's kind of a clear hierarchy of goals. It's always a kind of a quantitative trade-off between consequences.
Now, it feels to me, just an intuition, that part of that trade-off would be a probabilistic assessment of what the human goals would be next. But I remember you saying that you don't want to go there, so I'm feeling a tension.
Yeah.
Have you thought about this tension?
Yeah, you're right. If I know what humans' goals actually are, then I can make better predictions about the future, because I can use it to make predictions of what they do about what they do. That is a tension. That's correct. And so what I currently do is the robot is forming a prior for human behavior, which is basically averaging over all their policies over all possible goals. So this is a really, really, really uninformed prior about what the humans will do. Basically, assuming humans will kind of do whatever. And this is, of course, not a good prior, right? It might, I mean, we're talking about robots interacting with lots of humans. And for most of the consequences in the real world, the aggregate behavior of humans is way more important than who exactly does what. Well, this is also the argument that macroeconomists or neoliberal economists, neoclassical economists do when they say we treat all the humans as rational, even though we know they're not, because this is the as-if statement. We are only interested in the macroscopic behavior, and it's good enough. And I think the similar thing is true here. The robot, maybe it doesn't get the individual humans' actions right because it doesn't know what their goals are. But the thing that matters is more the aggregate behavior of humans, and it might get that sufficiently right to make sufficiently good predictions about what the future will hold. But you're right, there is a tension. We might imagine a system that distinguishes predictions about the future, which might be based on beliefs about actual goals, and the decision-making component that is not assuming humans have particular goals. So that's maybe a good idea. And I guess if we ask LLMs about what will happen if, then the LLM kind of implicitly will make assumptions about human goals. So it's already in there. In the world model, it's probably in there anyway.
Okay, great. Thank you.
We also had a
This
follow-up.
system. Sorry.
We had a follow-up in chat by Harry.
Yeah, Harry, you're right. There's no likelihood of goals in there. Eventually, we might want to have something like a different weights of different goals, but not in terms of how likely they are, but maybe in terms of how specific they are. Because when aggregating over goals, we might want to kind of give goals that are more broad, a larger weight than goals that are very specific. Because if we give the goal to get a very, very specific trajectory of the world that describes where every molecule is, if we give that too much weight, then eventually it might be a little bit more meaningless than if we rather consider much wider goals, like the planet is here rather than there. So there is maybe some weighting in there, but it's not really in terms of likelihood, but maybe in terms of specificity or something like that.
Would this system be able to infer the needs of the human? Let's say the human says that, hey, I want something sweet, and the system says, I think you are just hungry and I give you proper food. Or alternatively, for example, if the human says that I hate this other human and I want to harm them, then the system says that perhaps do you feel unsafe, and if I help you to become more safe, then you don't need to harm them anymore.
Maybe. I mean, the first example sounds like something that Geoffrey Hinton would like mother doesn't give you sweets. I find this a horrid idea. I want to make my choices myself. Maybe the AI should point out, are you aware of the consequences of the sugar? You might die earlier and therefore have less power in 50 years from now. And maybe this way it might come in and it might be protective, as in the self-harm example here, because sugar is some form of self-harm, but not in the sense of trying to figure out what the actual goals are. And so the other example regarding harming someone else, it would probably not allow that because it will disempower the other person, and because the aggregation across humans is really inequality averse. Killing someone else or disempowering someone else has a really high price in terms of the power metric, and so it will probably not allow that. David again.
Yeah, I really like that question because part of bounded rationality is limited computational ability, but in practice, a lot of humans know that they make poor decisions when they're hungry. And, this is a reason why it takes 2 keys and all these layers of buttons to send nukes, right? There's a lot of things where humans want there to be additional steps before they take more drastic actions. So I do kind of like this idea of a human agreeing to a situation where they say, there's certain actions that I have to sleep on, and that might be like a step 1 when you start interacting with these AI agents, like a precursor step, like a contract about how you're going to deal with each other. So just some ideas to throw out.
Yeah, that's a good idea. I mean, to a certain extent, the nuke example is probably taken care of by this finding here, that agent will probably ask a number of times back before they really allow this, or maybe not allow this at all, because knowing that it will disempower everyone else and that outweighs it. So, but yeah, maybe I should not understand what you just said, David. Thank you.
So we're about time today. So we will end the session now. But first of all, thank you so much for the presentation, Jobst, and thanks everyone for the discussion as well.
Yeah, it was really good.
Thank you.
Thanks for coming. Thanks for presenting.
Yeah, and point me to possible collaborators, please, or funders.
So thanks so much, and for everyone, see you next time.
Yeah.
Ciao.
See you.